Hello, this is Abell. The topic of our discussion in this video tutorial is Wronskian and differential equation. Let's begin this video with the definition of Wronskian. Wronskian of two functions f and gx is defined as the determinant of these two functions and it is a derivative. So this determines, this is a 2 by 2 determinant which we can calculate by multiplying the diagonal entries and we subtract them. So the Wronskian will be f of x times g prime of x minus f prime of x and g of x of these two functions. Now next take some examples and calculate the Wronskian of these functions. So my first example is if the function f of x is equal to x and the function g of x is equal to x e to the power x. Then the Wronskian of these two functions f and g, this will be a function of x, will be in the first row I will put the function. Doesn't really matter which order I put, but only matter that if I put in the first place the first function, in the second row the first place it will be its derivative, which is a 1. Derivative of the second function will be a product rule, so it's going to be e to the power x plus x e to the power x. Now if I multiply this, I get x e to the power x plus x square e to the power x, negative sign, multiplication of this x e to the power x. So there is some cancellation here, so this term will cancel to this. So therefore the Wronskian is x square e to the power x. So this is our final answer. Here I have one quiz problem for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. Next, I have some application of the Wronskian, which will help us in our coming video. So our first application is if you have a differential equation of this form, which is a homogeneously differential equation of variable coefficient, and the leading coefficient is 1. So there is no coefficient of y double prime. And if it has two solution, these are the two particular solution, and they satisfy the differential equation, and then they will form a general solution to that differential equation if and only if the Wronskian of that differential equation is, the Wronskian of these two solution is non-zero. So that is the if and only if condition. If the Wronskian of the two non-zero solution is non-zero, then they will form this general solution. And if there is a general solution, their two parts of these particular part of these solutions will have non-zero Wronskian. Then there is a definition. If the Wronskian of two particular solution is non-zero, then we will call these two particular solutions the fundamental set. So for example, if y1 and y2, they are two solutions and their Wronskian of y1 and y2 is a non-zero, then y1 and y2 will be called fundamental set. So this is the definition of what is a fundamental solution set if the Wronskian is non-zero and they satisfy the differential equation. Here I have one more example. In this examples, we have given two particular solutions and we will check that whether they will form the fundamental set of solution for this differential equation. So first we will verify that the y1 and y2 are the solution of this differential equation. So let's first check y1. So if we want to check y1 is the solution of this differential equation, first we need to calculate y prime and y double prime. So y1 prime of t therefore is equal to 1 half t to the power minus 1 half, and y double prime of t will be minus 1/4 t to the power minus 3 half. So these are the two derivatives. Then we will plug these derivative into the differential equation. So therefore 2t square times y double prime is 1 4 t to the power minus 3 half, and then plus 3t times y prime is 1 half t to the power minus 1 half, and then y minus t to the power 1 half. This must be is equal to 0. Let's simplify this. So this gives you 1 half, and this gives you t to the power 2 and t to the power minus 3 half is basically 1 half, because 2 minus 3 half is 1 half, and here you get 3 half and t to the power 1 half, and minus t to the power 1 half is equal to 0. So as you can see, this and this become minus 3 half, and this is a plus 3 half, the middle term. So they cancel to each other. So all these things cancel. So 0 is equal to 0. So in fact, this is a solution to our differential equation. Similarly, we will verify that y2 of t, which is a t to the power of negative 1, is also a solution. So we calculate y2 prime of t minus 1 t to the power minus 2, y2 double prime of t, which is minus minus plus 2 t to the power minus 3. And now we will plug everything into the differential equation. So let's plug it here. So 2t square y double prime is 2t to the power minus 3 plus 3t y double prime is a minus t to the power minus 2, and then this is a t to the power negative 1 is equal to 0. So this will become 4t to the power negative 1. This will become minus 3t to the power negative 1, and this is the t to the power negative 1. This will become 4, that's a positive 4, so 0 is equal to 0. So we have verified that these are the two particular solution of our differential equation, y1 and y2, and they will form the fundamental set of solution if their Wronskian is non-zero. So next we will calculate the Wronskian of y1 and y2, which is equal to y1 t to the power 1 half, and y2 is a t to the power negative 1. So derivative of this is a 1 half t to the power minus 1 half, because 1 half minus 1 is minus 1 half, and this is a t to the power minus 2, negative sign in the front. So now cross multiply. So this is going to be a t to the power 1 half times t to the power minus 2, and minus 1 half t to the power 1 half and t to the power negative 1. So this Wronskian, if you simplify, that will be 1 half minus 2 is going to be a minus t to the power minus 3 half, and here minus 1 half t to the power 1 half minus 1 is minus 3 half. So therefore your Wronskian is, if you combine them, is a minus 3 half t to the power minus 3 half, which is not equal to 0 because t is strictly positive. Therefore, the y1 and y2 form a fundamental set of a solution for our differential equation. Next, I have one more quiz problem for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. Next, we have very important theorem, which is known as the Abell Theorem of the Wronskian. So, Abell Theorem is states that if you have a differential equation, homogeneously differential equation with a variable coefficient, and it is in this form where the leading coefficient is 1, then you can use this formula to calculate the Wronskian of that differential equation. And in fact, if the Wronskian is either 0 for all interval where the solution exists, or else is never 0 in on that interval. So C is here is a constant which depend on y1 and y2 but does not depend on t. So more importantly, this is the formula of the Wronskian if the differential equation is written in this form with the leading coefficient 1. Let's do one more example where we will calculate the Wronskian of the solution using the differential equation, not using the solution, and then we will verify that basically in fact these solution will give us the correct Wronskian. So here we have the differential equation, and I will write this differential equation into a standard form by dividing 2t on both sides. So solution. So first we will write it leading coefficient 1. So therefore 3t divided by 2t square y prime minus 1 over 2t square y is equal to 0. Now from here we can calculate the Wronskian by using that formula. So W is equal to C times e raised to power negative integral of this term, which is a pt. If I simplify this term, this is a 3 divided by 2 and 1 over t dt. Therefore, this is equal to C e raised to power minus 3 half times natural log of t. And this can be simplified to e to the power natural log of t to the power minus 3 half. Therefore, this is equal to e and natural log will cancel. So this will be c times e to the power minus 3 half. And this is the same example where we calculate the Wronskian of these two functions, these two solutions, t to the power 1 half and t to the power negative 1. And we get this time 3 half t to the power minus 3 half. So this verifies that the Abell theorem, if you calculate the Wronskian by using the Abell theorem, the only thing you will not recover is the constant, but the rest of the Wronskians will be the same if you calculate if you know the solution and you calculate from the solution by using the definition of the Wronskian. Here I have one last quiz problem for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. This is also the end of this video tutorial. Thank you very much for watching. I will see you in the next video. Bye for now.